I hope you can see.
Perfect. Thank you, Rainer.
Yes, okay. So good morning and welcome to my lecture, which is entitled Modeling, Monitoring and Vibration Control of High-Performance Turbomachinery. I would like to subdivide my lecture into the different parts. I first will give a short introduction. Then I speak about vibration phenomena in high-performance turbomachinery, followed by the three main parts: modeling, monitoring, and vibration control of high-performance machinery. You may ask, why did I select these three topics? Well, the story of each machine starts with the design of a machine, and in this phase, modeling and simulation are important tasks. Then, during the lifetime, a safe and reliable behavior is expected with a high availability of the turbomachines, and monitoring and diagnosis are important tasks during this lifetime. And if vibration problems occur and will be detected, the third part of my presentation will be to find a solution. And this means how can we control the vibrations? And to manage these three important tasks, the optimal design of a machine, the monitoring during lifetime, and the vibration control during operation when problems occur. For this, we need good models describing the essential physical effects, and these models are more and more needed in all phases of the machine's lifetime. And such models should be available in all stages of the lifetime of a machine as a so-called, today we say, digital twin. In other words, a good model should be a part of the machine in all phases of lifetime. Now, in this first figure here, we see a turbo generator with a large steam turbine and the generator. And in these machines, of course, there are different disciplines to consider. Of course, thermodynamics, mechanics, electrodynamics. And I will concentrate here on the mechanics or vibrations part. And this can be subdivided more into the part stresses, strength of materials, and also to the part I will present today to lateral and torsional vibrations or rotor dynamics. And I will concentrate in my lecture mainly on lateral. This is due to time limitations. And this rotor dynamics parts, there are also some keywords. For example, we know critical speeds, unbalanced response, air gap torques are important for torsional vibrations, stability problem due to oil film or seal excitation. So in this next slide, we see a cross. We can look into a machine of a turbo machine with a turbine shaft drain. And in the center of the machine, are the rotating parts with the different steam turbines, low pressure here and high pressure on the left-hand side. We don't see the generator here. And regarding the vibration problems, the vibrations are mainly coming from these rotating parts. And some data you see here for this machine, though it's large power and shaft lengths and weight and so on, and bearing diameter. The question is now, which vibration phenomena are of importance in such high pressure, in such high performance turbo machines? This example here, well, this is not a power plant machine, it's an industrial turbine. However, I want to explain which components are of importance and which forces. Forces are very important for our vibration problem. So regarding the components, that's what we have in all machines. It's a rotating shaft with the blades. That's in the center of this picture here. Then, of course, there are influences from foundation, pedestals, bearings, here and of seals. So these are, I think, very important parts when we consider the vibrations. And regarding the forces, first of all, there is, of course, the rotor weight. Well, you may say rotor weight, this is statics, has no influence to the vibrations, but this is not the case because the rotor weight influences the static position in the oil film bearings, and with that influences the dynamic behavior of the bearings, stiffness and damping coefficients. There are other forces, process forces, very important here, the unbalanced forces, and in the bearings, the bearing forces, reaction forces, seal forces, and bearing forces, and they are very important as well and can be expressed by some stiffness and damping behavior. Now, the question is, why do we need rotor dynamics? And they're connected to this are different more questions, and I will sum up this here. How is the influence of time-dependent forces and moments on the dynamic behavior of a machine? Which motions of vibration and which internal stresses act on the rotating and the non-rotating machine parts? Are there critical conditions like resonances, instabilities possible? Can vibrations destroy machine parts? Let's consider rubbing, blade loss, shaft cracks, bearing failures, large deformations, and so on. And finally, and I think this is very important, which interactions have to be considered. So it's not the rotor alone, the shaft line, but there are, as we have seen, fluid structure interactions in bearing and seals, rotor structure interactions between the rotor and the bearing pedestals and foundation, rotor blade interactions, and electromechanical interactions when we think to the electrical machines, generator, for example. Now, let me come back to this system, which we can see here. The main parts, of course, the rotating parts are the turbine rotors and the generator, which is not shown here. And we have two types, mainly in these machines, of vibrations. These are the lateral vibrations, so that means vibrations perpendicular to the shaft axis, lateral vibrations, and we have torsional vibrations of the shaft frame. So in our machines, usually, because we have no transmissions or gears in our system, there is no coupling of lateral and torsional vibrations. This is usually the case, so we can separate this. And to look further in my lecture, I will concentrate on lateral vibrations here. Now, anyhow, in this first overview, I will consider both lateral and torsional vibrations and first start with lateral vibrations. Which phenomena are of practical relevance? Now, lateral vibrations are perpendicular to the shaft axis with bending along the shaft line. And the physical effects are inertia, that means masses, stiffness and damping of the system components, that means in the shaft, the bearings, and the foundation. And the next question is, what are the typical dynamic characteristics? So we have to consider natural frequencies, critical speeds, how are the natural modes? Do we have stability problems? And how are the amplitudes and phases at the shaft system in the vibration response due to excitations? And finally, come to the excitation. This is mainly mechanical and thermal unbalances, bow, also unbalanced due to coupling errors, and excitation due to instabilities in fluid bearings and seals. So that's main characteristic of the lateral vibrations. When we look into the torsional vibrations, they are around the shaft axis with torsional deformations along the shaft line. And the physical effects, again, there is inertia effect, moments of inertia. We have a torsional stiffness and damping of the system components. It's mainly the shaft line. And the dynamic characteristics are, again, natural frequencies, now torsional natural frequencies, natural modes. We have damping. Unfortunately, in the torsional vibrations, damping is very low. That means if something happens and there is vibration, the decay is very low. Furthermore, amplitudes and phase angles, also the vibration response due to excitations is an important dynamic characteristic. And the excitations are mainly here coming from the air gap torques in the electrical machines due to electromagnetic coupling in the generator and in the grid. Now, I mentioned before already, in large machines like this, of course, in the center is the shaft line. It's beam-like, consists of beam-like elements along the shaft, and we can model this in this way. However, to have a good model, we have to look for different interactions which have an influence on rotor dynamics. And I subdivide here into the left side and the right side. On the left side, we look what is important in coupling of the lateral vibrations of the shaft line. There is of importance the rotor fluid interactions in oil fin bearings and seals. We see a tilting pad bearing, for example. Furthermore, and this is known since long, that also there is a rotor structure interaction, for example, with casing, foundation, pedestal, and so on. And we should consider this when we look at lateral vibrations. On the right-hand side, torsional vibrations around the axis. There we have interactions, of course, with the electromechanical system in the generator and in the grid. And there are air gap torques acting in the generator, which excite the rotor shaft line to torsional vibrations. Another effect is the rotor blade interactions, especially in the last stages of the low pressure turbine. So there may be bending of the blades, and this bending of the blades interacts with the torsional vibrations of the shaft line. Now, after this introduction into the different phenomena in high-performance machinery, I will now come back to the three main parts. That was the modeling, the monitoring, and the active and passive vibration control. And I will start now with the modeling part. And I have subdivided this into modeling of a very simple shaft, the so-called Laval Shaft, and then modeling of high-performance turbomachinery. So let's start with the Laval Shaft. It was Gustav de Laval, a Swedish engineer, who started to investigate the rotor dynamic of this simple rotor of a steam turbine. So we see here this rotor system, the steam, and the simple system here consists of an elastic shaft, beam-like shaft, and the mass, the so-called, in Germany we say Laval Laufrad or impeller. And now, as I said, this is a very simple vibration system consisting of a spring or elastic part and a mass part. And when Gustav de Laval started his investigations, he thought, when I increase the speed, so this is here amplitude versus speed shown, when I increase the speed, then the unbalanced forces, m omega squared, will increase, and so vibrations will increase. It's dangerous. I have to stop at some time. But then he saw vibrations went down again, and he was very astonished about this. And we know today, after this resonance, we are going to a so-called self-centering effect. So this was a very, very important investigation that Laval made. I come back, and later on, I think it was 1895, there was a theory by Vöppel that could explain this behavior in a model. And the model looked like this. This is a very simple model. So it's a as I said, called Laval Shaft in the United States. They say it's the Chevcot rotor. In Russia, I think it has another name. However, for us, it's the Laval Shaft. And it consists of this elastic part, a beam. So it's like a spring, and the mass. And we have forces, unbalances, and mass eccentricity multiplied by omega squared. Here I consider rigid bearings. And in this simple model, we can define the equations of motion, consisting of inertia part, damping part, and stiffness. Damping may be coming from material damping or whatever. And on the right-hand side, and this is important, if we look at the two directions, x and y, we have excitation force, so that's coming from the unbalance, and we have frequencies of excitation, which are the rotational frequency omega. So this is important to know. Now, if we investigate this system, we come directly to that, what Gustave de Laval investigated in his tests. And we can see it by this formula here. So it expresses the vibration response in the center where the disk is versus the speed. So we have increase of vibrations because unbalance increases. Then we come into a resonance. In this case, this part here is becoming zero, and we have in the denominator zero. That means very high amplitudes. And then this sign changes here, and the vibrations go down again to the self-centering effect. What we see in this picture also, there's a resonance, and this resonance is determined by the parameters of the system. That means the stiffness and the mass. And we also see when we increase the damping, so in this direction, we can influence the vibrations in the resonance. Higher damping leads to lower vibrations. Coming back to the resonance, we know the natural frequency of this Laval shaft is very simple. It's square root of stiffness divided by mass. And now if the excitation of frequency, omega, rotational speed, rotational frequency, is equal to this natural frequency of the system, then we have the resonance case. And this is what Laval has also seen. But then later on, fortunately, vibrations went down again. Now, in this first model, we did not consider the behavior of the bearings. And in today's machine, we know these machines, these large machines are running in fluid film, in oil film bearings. Sommerfeld number plays an important role here for the different operation conditions. And we know today that the stiffness and damping behavior of the bearings play an important role besides the other parts, so stiffness of the shaft and the mass term. Now, to explain it a little bit, first of all, we have this static. I speak about horizontal machines. Horizontal machines have a weight and they act on the bearings. And due to this weight in the bearings, we have static bearing forces. And the oil film has, or the shaft in the oil film has a special static position. So this is the center of the bearing, and due to the weight, we are, let's say, at this position. So that's static. But now there come, in addition, dynamic forces due to unbalance, due to other forces. And then we will have, and this is a very simplified vibration behavior, vibrations around this static position, here shown as an elliptical orbit. And when we have this additional motions, then there will be also reaction forces coming from the oil film to the shaft. I call them here Z1 and Z2. And we know today in a linear theory for the fluid film bearings, we can express these forces by a system of stiffness coefficients and damping coefficients. And this is a very special system, not usually as normal stiffnesses. It expresses the stiffness and damping behavior of the oil film, stiffness coefficients, damping coefficients. What is the effect of this additional influence of the oil film bearings? I start here to show again the behavior of the rigid bearing. We have seen before in Laval's investigation, we have increase, resonance, and then coming back to the self-centering effect. Now, if we include the oil film bearings, there are different effects. First of all, the system becomes weaker, and due to this, the resonances go down. But now we have two resonances, and this is because we have different stiffnesses in different directions. So low stiffness, higher stiffness. So we have two resonances. They do not always occur, but I show them here. And the other effect is due to the oil fin bearings, we have more damping maybe in the system and the vibrations are reduced. So there are some positive effects. However, we have to consider also that unstable vibrations may occur at higher speeds. And you see it here, the lateral vibrations may, due to this instability, increase. And this is, of course, something what we don't like. And the question is, where's the energy coming from? Of course, we know we have rotational energy in the shaft. This is transferred to the oil film. And the oil film gives this energy back into the lateral vibrations. So this may happen at higher speeds, but we have to consider this. To summarize the influence of oil film bearings, we have additional stiffness, damping, we have anisotropy, and we have danger of self-excitation. Now, where do we get the stiffness and damping coefficients from? They can be determined by numerical calculations or by experiments. For a bearing with a special geometry, the coefficients depend on the Sommerfeld number. There are all the important parameters of the bearings included, like the static force, the viscosity, which is an important part, the rotational speed, and so on. We have to recognize that fluid film bearings have usually anisotropic behavior. So that means K11 is unequal K22. Same for the damping. And very important, the coupling coefficients differ from each other as well. K12 unequal K21, and for the damping as well. And important to know, a measure for instability sensitivity is this difference here of these coefficients. Damping coefficients help to have good stability behavior. All these coefficients can be found in tables or diagrams. I show here a short picture about a test rig. That was an investigation we have made at Darmstadt University to determine the stiffness and damping coefficients of bearings by testing. So this test rig consists of a shaft that's driven by a motor, so it's rotating. In the center, we have the test bearing, some test bearing with some geometry. And then the speciality of this test rig is we have two bearings, but these are magnetic bearings. And by these magnetic bearings, we can excite this rotor to lateral vibrations in both directions or only in one direction. And due to this, these forces occur during operation in the oil film. And they can be measured. First of all, we need displacement measurements, but then we need also force measurements. And these force measurements are made in these magnetic bearings with so-called Hall sensors. So this was a very nice procedure, testing to find out bearing stiffness and damping coefficients. Now, I would switch from this first simple model, but this was the beginning by Laval, and therefore it's very important. How do we consider modeling of high performance turbo machinery today? And as I said, I think it's very important to have these good models, very good models, also during lifetime. Now, what we have to consider, the different interactions. I will consider now only lateral vibrations of this shaft line, that means bending. And I need to include, in any case, these rotor fluid interactions and rotor structure interactions. And I will show this now. So our model looks now much more complicated than before, than the Laval Shaft. And we have to include all the stiffness and mass terms along the shaft line. We have to include, shown here by this blue, damping and spring, the oil film coefficients, the pedestals. Then there are springs between the pedestal and the foundation, and we can include also the foundation. I will show how this can be done. Now, the equations of motion shown here for lateral vibrations consist of mass, damping, gyroscopic stiffness matrices. Here are the bending displacements and the bending angles, and here are the force vector, the excitation, mainly unbalanced. So, as said before, oil fin bearings are important to include. And in this picture, you see along the shaft line where bearings are located. And there are different types of bearings like cylindrical, elliptical, three-wedge bearings, tilting bed bearings, and so on. And all these bearings have different coefficients, so they have to be considered, and they are used to optimize the dynamic behavior in such a turbine train. The next important effect is the rotor structure interaction with the foundation, for example. We know foundation couples with the shaft train. And typical for foundations is that there are many modes in the speed range, and there are significant coupling effects between the bearings, from one bearing to another. There's coupling, and also in horizontal and vertical direction. So it's not only for each location at the bearing one effect, but there are coupling effects. So all the dynamic effects are coupled in the system. Now, how can we consider these foundations in overall model, including the rotor, the bearings, and the foundation? Now, it starts with the finite element method for the dynamics of the foundation. So it's a large system, of course. And the procedure is to estimate, in the first step, the mode shapes and the natural frequencies of this foundation without the rotor. And we can calculate frequency response functions, especially at the bearing locations. And then we couple these frequency response functions of the foundation without rotor to the rotor system. And we can calculate these frequency response functions by the mode shapes and the natural frequencies, which have to be determined in the first step in this finite element method. And when we have this information, then we can build up the frequency response functions at the bearing locations, at the coupling points between foundation and shaft line. And this is how such a frequency response functions of the foundation looks like. So it has many, many resonances. And you can imagine that these effects are important to include. So as I said, they can be found, the frequency response functions, either by finite element calculations, determine the mode shapes and natural frequencies, and then to couple them with the rotor part. If measurements are available, but this is possible as well. Now, if we have these functions, we have here the rotor train, the bending part. We have the oil film also included. And now we can couple this system of frequency response functions determined for the foundation only at the different connecting points between the rotor and the foundation. And we can calculate the overall system, including all effects, shaft line, bearings, foundation. Now, when we have all this done and we have built up the model with all effects, then we can calculate, of course, different things. For example, the eigenvalue problem for such a turbo generator. leads to the eigenvalues expressing the damping behavior and the natural frequencies. There's also information available regarding the stability. Here are some examples for the mode shapes for a large machine. So there is 10.7 Hertz with a corresponding damping. It's mainly in this low pressure part. Then we have another typical generator, first bending at 11 Hertz with the special damping. And here's a higher mode at 27.6 Hertz. The other part, which is of interest in the design and in the calculation, is the unbalanced response of large turbo generators. Now we have the model again here, but with unbalanced excitation, which is shown here on the right-hand side. And we can determine the response again. And this is expressed now in this curve amplitude versus rotational speed. That's for a half-speed machine. Running at 1500 or 25 Hertz. And we see here, due to unbalanced forces, how the response of amplitudes looks like when we are in the range between 10 to 15 Hertz. We have some higher amplitudes up to 100 microns in this calculation. And the excitation was at this location. So we can do different calculations to see how the behavior is of our machine. Now let's come to the next part, to the monitoring part of high-performance turbo machinery. And I will subdivide this again into conventional monitoring as we do it today, and an idea how a future model-based monitoring and diagnosis could look like. I start with the conventional monitoring. That's what most of you know, I think. For monitoring in such large machines, absolute vibration velocities in millimeter per second are measured usually at the pedestals, and relative shaft vibrations in micrometer are measured at locations of the bearings. So that means between the stator part, the bearing, and the bearing pedestal and the shaft line. And these values are measured and can now be evaluated by, for example, ISO standards to see whether we are in the allowed range or not. Now, if we consider relative shaft vibrations, which are measured with some sensors in horizontal and vertical direction, for example, we can do a superposition of these two signals. So here it's simple case unbalanced, it's harmonic vibration. That's not always that nice as we see it here. But if we do a superposition of these two signals in vertical and horizontal direction, we come to an orbit where time is a parameter along this orbit. And you can consider this orbit as, when you look along the shaft line in axis of the shaft line, you see the vibrations at this special location where you measure. And this is also something which is considered in the monitoring. Very helpful are also such run-up and run-down curves when the machine is run up or run down. We know now over the speed range from 0 to the final speed where the resonances are, how the damping behavior is. Here it's shown, for example, for bearing number 5 of the machine, the amplitude, and here the phase. So this is also very important to see where are our resonances. And also very helpful are frequency spectra showing not only one side of the spectra, that means this side here, but also in this double spectra where we see the forward and backward frequencies. Both are also very helpful to analyze vibrations and to diagnose failures. Now, some ideas about how could a future model-based monitoring and diagnosis look like. And this we have tested not at a high-performance turbo machinery, but at pump system. First, I want to show the basic idea. What we usually do in monitoring is we measure if this is our rotating system, we have input forces, unbalanced, other forces, and so on. And we measure the response. So this is what we usually do. We have this response only. We don't measure forces at the input because it's difficult to measure forces, all the forces. So we try, in case we are looking for a failure diagnosis based on these output signals. Now the idea is, could we have additional information about our system in terms of, let's say, frequency response functions between one input and one output, or different inputs and outputs? And this would, if we know the input force, if we could measure the input force and measure the output, we could determine such frequency response functions. We have now a relation between the input, the output, and the system behavior. So if it would be possible to have some test signals at the input, of course, I know this is difficult. We can't measure balance forces and other forces, but if you have some test input forces, we could determine such frequency response function. And by this, we would have a good model of our system, which is measured now. And based on this model, a parameter estimation and estimation of failures would be possible. So this is an idea about future model-based monitoring by means of frequency response function. Of course, one question is, how strong is an influence of failures on the frequency response functions? In a research project of Technical University of Darmstadt, we have tested this not for high-performance turbomachinery, but we have done it for such a pump system. And this pump system, driven by a motor, we see here the impeller of the pump and here the bearing. This had a special bearing system, and this bearing system have been magnetic bearings, of course. Well, this is not the usual way to run this system, but in our testing we did. So what was the idea now? We have forces in our system and we have forces in the magnetic bearings. What we did, we introduced additional test forces. We defined these test forces into the magnetic bearings and we measured the response. So we excited the system with special forces. We could measure these forces by hole probes in the magnetic bearing. And then by this way, by sensor measurement and actuator characteristic of the magnetic bearings, we could determine frequency response functions of the system. And the idea was, can we see if something changes in the system by means of these frequency response functions, what has happened inside the machine? So we would have much more information about the internal life, dynamic life of the machine when we know these frequency response functions. An example is shown here, very simple example. You see here in this dark blue curve, the normal operation behavior. Well, this system is well damped. You see here some resonances, but with very high damping due to the fluid. But then another curve, this is this curve here, and something has happened. And what has happened here, of course, we tried to find out what happens if you have a dry run, no water in the pump. And we could see the difference here. This is, of course, an extreme case. Normal operation, dark blue, and dry run here. So that gives an alarm. You have no water in the pump. As I said, this is a very simple example. But you see here the frequency response function, amplitude versus frequency up to 800 Hertz. So we did different other tests where we have introduced failures, and we had always some characteristic. How does our system behave? Now let's come to the last part of my presentation, which is the vibration control of high-performance turbomachinery. And I also subdivide this now. I give first some general introduction, and then I have some examples about passive and active vibration control. Well, first, the general part. There are different measures or possibilities how we can control vibrations. This is independent whether we have passive or active control. So first of all, reduction of excitation is one part. That's always good. Then system tuning, changing of mass or stiffness in the system. Introduce damping. Can we add some dynamic parts to the system to have a so-called vibration absorber? Or can we, by definition of special stiffness and damping values at some locations, some isolation of the vibrations? This can be in both directions. We can protect the surrounding of our disturbances, or we can protect our system in instruments, measurement instruments, for example. Now, as I said, this can be done passive, as usual, or we can look also whether there are extended solutions by active vibration control. When we go in this direction, there is, of course, an increase of effectiveness when we go in this direction, but also of complexity. And there, on the other hand, more solution variants. Let me show a first simple example, which you all know, reduction of excitation. So this was the first measure. And this is, of course, a passive vibration control. We see here the balancing of a low-pressure turbine going into the balancing unit. And here we see some balancing weights in the circumference of the rotor part. So as I said, this is passive vibration control. However, for the same type reduction of excitation, there are solutions available today which work with an active vibration control. This is not available for high performance turbo machinery for these large machines, but for example, for machine tools, for grinding, for example. Now, what is the procedure with this? We have a system, at the running system, this active balancing device, and it consists of two discs that can be rotated in opposite direction. We see it here. This is the first disc, second disc, and we can move during operation these discs with these unbalances here. And so we can find out where do we need additional compensation balances, and then we can rotate these two discs in order to have a good solution. So this is active part of vibration control. And maybe in the future we find some solution also for large machines. Now the next part is a passive vibration control, and I show it again for the simple Laval shaft. This is tuning and damping. Now what we can do, can, for example, increase stiffness or reduce mass. That's a tuning effect. And on the other hand, we can increase the damping, which was shown before already. When we increase the damping, the amplitudes go down. The tuning effect is, for example, possible by shifting resonances. When I increase stiffness, I shift the resonance, or when I reduce the mass. Now, another example of passive vibration control is shown here in this rotor test rig for a low pressure shaft of an aero engine. By the way, this is the low pressure shaft of this Airbus aero engine for the A400M, I believe. We tested this low pressure shaft, only this low pressure shaft, in the lab. And you see here there's no bearing. That's a long distance between the bearings. And this is because there are other shafts around this low pressure shaft. So there's no possibility to have a bearing here. Of course, in the test here, we have a bearing. It's not a bearing, it's, well, to avoid contacts. Now, the speciality of the system is there is a turbine part here, but this is a dummy for the turbine. It's a disc with the same mass. And of course, in this part, dynamic behavior is very important. Therefore, we have two bearings here. These are cylindrical bearings.
Sorry, Finite, one more minute.
Yes, I will close. Okay, I will show how we can realize passive damping by means of squeeze film dampers. They are located here between these bearings and the housing. And the idea is, by this passive damping, we have the outer ring of the bearing and the casing, and between there's the oil film. And if there are vibrations, then the oil film is squeezed. Now, this is, shows you some insight into this test trick. And now this worked quite well, but we also tried to use active damping with piezo actuators. So we changed the squeeze film dampers by piezo actuators at the bearing locations with the advantage of active damping, optimization in the entire operation range, diagnosis, failure identification, no oil supply, and a first step into more electric machines. That's how it looked like. This has, of course, especially for aero engines, some disadvantages, weight, and so on, and additional effort expenditure. We need, for this active solution, a control loop, and we need, as I said before, again, a model. So in active vibration control, modeling is again very important. And I show at the final end a result, a comparison of the passive and active solution. We see here the orbits for the passive case and for the active case. So there was a reduction of 60% by this solution. And of course, as said before, the costs and expenditure are high, and we have to consider the weight as well. Now, I close this session, well, sorry, not the session, my lecture, Modeling, Monitoring, and Vibration Control. My idea was to show that modeling, and a good model, is very important for the design during lifetime, monitoring, and if problems occur, for vibration control. And I think this could be the future, to have better models that can be used in all cases. Thank you very much.
Thank you very much, Professor Rainer, for a very interesting presentation. It's always good to have the theory background and up to implementation in the plants, and also how to monitor the vibrations at site. So thank you very much for that.
Yeah. Okay.
I think we have time for a couple of questions. The breakout session will start at 9:45, so I think we have time for a couple of questions.
Is it now in this session, or do I have to go to the meet? No, I don't know.
I guess according to the, perhaps you can correct me, Monica, but I guess from the session we start at 9:45, or Monica?
It starts as soon as possible.
Okay.
Okay.
So yeah.
May I ask a question?
Yes.
Yes.
Rainer, I would like to ask you, I mean, we know that we will see a future with more flexible operation. What would you say are the main challenges for the Nordic plants in this respect? Looking at turbine and generator vibrations.
Yes. Well, I think more and more for this is important, because if you have more changes, when I understand you right, flexible operation, the dynamic of the system is more and more important to consider. So I think all these additional changes you will have during operation bring time-dependent changes, forces, moments, and so on. And therefore, good models are very important to include again. I don't know whether I kept your question right.
I mean, we have seen a development for the German plants, that they are really delivering flexible operation. But when you discuss with them regarding, for example, wear and tear, it's quite obvious that they are aware of the fact that they have quite short remaining operation time.
Yeah.
But for the Nordic plants, we see a a quite more years of operation ahead of us. So we don't want to take decisions that will jeopardize the plants, of course.
Yeah, I see. Well, in Germany, for example, we have now many gas turbines running with flexible operation. And in this case, there's one problem, for example, when you run up and run down, there are thermodynamic effects and unbalances and so on. So, but this is operation of gas turbine types, for example. But in general, I think your way to keep this high performance turbo machinery in your plants, from my today's view, is a correct way. And some people discuss here in Germany, was it correct to close this, from my point of view, safe systems, nuclear plants? So there's a big discussion again whether it should come back. It will not come back in Germany, but there are new ideas about nuclear power plants. And it's interesting to see and to follow what will happen in the future. So I think your way is the right one.
Thank you, Rainer.
Thank you. Are there any other questions? Because I can ask you, Rainer, we did a couple of years ago had a project in the Energiforsk program where we did modeling of a turbine train, and then we did measurements on the plant on the corresponding turbine train. What can you say? What is the main difficulties when finding a good agreement between modeling and the actual measurement out on plant?
Yeah, I think in both we need improvements. I think I hope I could show today that improvement in modeling is very important by introducing all effects that are important. One is, for example, the foundation, which in the past years we observed has a very large effect. On the other hand, when you look at the experiments and observation in plant, I think it's good, and I wanted to show this by the conventional monitoring. But maybe what I said before, if we have more information about the inside, the dynamics of the machines, not only the output signals that show a lot, but you can determine more. But this needs, of course, some effort regarding force measurements, for example. And I'm sure in the future, it will be more and more by development of sensors, also force sensors and possibilities to measure forces. It will be a possibility to improve also the experimental investigations. So, and from both sides, we can come together, modeling and also experiments. And therefore, this was always my idea, also when I worked at the university. We need both. We need good models and we need good experiments. So this is, I think, what we can do. Improvement of modeling and improvement of experimental investigations, even in the plants, not only in test rigs.
Yep, good. Thank you for that. I think we have a last question here before we go to the breakout session. So please, Elisabeth.
I mean, 30 years ago, we had this type of model, measuring and modeling together when I started. And then I made quite a few measurements that was to be incorporated with the modeling. And is it that we have forgotten about this work done very many years ago, or is it something that you haven't done? We did it in ABB Stahl 30 years ago.
Well, I think by the time in modeling as well as experimental, there are improvements all the time. So we have better solutions available today. And I think in former times, what you mentioned, we didn't have these good tools. And I remember in my time when I worked for Alstom, we introduced this possibility to include the foundation, for example, and we were surprised how big this effect was. So it's done today usually in a procedure, and I know from the results there are improvements. On the other hand, there are always new effects occurring, and we have to study in research also which are the new effects and did we include it. A very important part is, and I can say it always, if you build up a model, you have to need to include all the important physical effects, and maybe there are new effects. We try to improve on both sides, but also on the experimental part. And maybe what you mentioned, that your comparison was not quite good. We were not in the position to have the best solutions on both sides. That's probably the case.
We had quite good solutions and quite good correspondence between the measurements and the calculations after tweaking the model a little bit. And I don't feel this is new at all. We did it on Oskarshamn 3 10 years ago or 15 years ago, when the foundation was more weak than expected. Then we did it wider. So I don't see that this is new, but it's interesting to take it up again.
Well, I would mention another point. I said important is in the modeling to include foundation, but also the bearings. And the bearings, I think, is always still some uncertainty. We have, of course, data in tables available, but these have been determined also in some test rigs or by calculations. And this is also not always very perfect until the end. So, and during operation, there may be changes regarding the clearance, regarding the temperature and viscosity and so on. So these are, I think, some uncertainties, especially in the bearings. The shaft line, I think we know very well. And this is because we do also measurements for the part rotors, modal analysis, and compare modal analysis measurements with calculations. There's a good agreement up to 1 to 2%. So the uncertainties are in other parts, bearings, maybe foundations. So this is what I would say today to the situation and to your comparison.
Yep. Thank you very much for that. I think we can continue the discussions in the breakout session. So now we take a short break here in the main session, and please come back some minutes before 10 o'clock where we start with the next presentation. So please click on the other link that Monica sent you. The link to discussion, and then we can have a further discussion with Professor Rainer Norman. So please welcome to the discussion forum.
Okay.
Ja, hör du mig Jessica?
Ja, visst, det gör jag. Hör du mig?
Okay, good. And I'm back in the main session. Just want to check Åsa and Jessica. Are you ready to start in a couple of minutes?
Yes, we are. Can you hear us?
Yes, I can hear you. Perhaps you can just try to share your screen so we see if that's work also.
Yeah.
It's already sharing.
Okay. Yeah, perfect.
Yeah, you can see my presentation, or
Yes, perfect.
Yeah.
Thank you.
yeah.
And I put the link to the report in the chat.
Good.
Thank you.
Perfect. Just wait 1 minute more so we don't start before the set time. Yes, I think it's just a couple of seconds before 10, so I can just start with a short introduction. So the next presentation will be on vibration measurement pitfalls, and it will be performed by Åsa Collé and Jessica Fromell from Efterklang. They have been working in this project, and also have been working with some project previously in the Energiforsk program. And I guess one of the projects you worked with some years ago was how to measure vibration, more of a guideline. But now we did the opposite way to try to identify on how to not measure vibrations, but more or less to find pitfalls related to vibration measurements. So it's a bit a different project, but we think it's very interesting to be aware of what kind of pitfalls you need to be aware of when you do the actual measurements out in the plant. So please, Åsa and Jessica, go ahead with your presentation.
Yeah,
Thank you.
Thank you.
I'll just
I give the word to Jessica first here.
Yeah, just turn on my screen and say hi, and then turn it off again, so maybe it won't interfere with anything. Okay, as Tobias said here, this is about collecting information about vibration measurement pitfalls when doing vibration measurements. And just a little bit short about Efterklang and about us that have done the project. Efterklang is originally Ingemanson technology, started in 1956. And in 2006, we were acquired by AFRY. And today we are called Efterklang. Efterklang is a trademark in the AFRY group, so to speak. And we are about 130 people working solely with acoustics, sound and vibration, and sound design. And we're located in Sweden, Denmark, Norway, and also Switzerland. And the people that have performed this study is me, Jessica Fromell, and my colleague Åsa Collé, and also another colleague called Christer Larsson that has helped us with revision and text and so on. Okay. So as Tobias described, the objective is to assemble knowledge and experience in the area of vibration and vibration measurements and the pitfalls that one might encounter when doing vibration measurements. And this study has been done and is a summary of a lot of different areas. So it's a summary of interviews that we've done with the Nordic nuclear power plants, and also a summary of literature studies and our own experience from Efterklang within the field, since we've been doing vibration measurements for quite some time. And this was performed by, we sent out a questionnaire before the interviews that everyone could prepare and answer. And we also did interviews over Teams this time due to COVID with each nuclear power plant specialist group. And this is what we're going to present during this presentation. So, okay. So the questionnaire is consisting of, for example, how to measure response vibrations and pitfalls when you measure on machine pipes, foundations, etc. And also pitfalls when you measure reference signals and you have force inputs. And pitfalls when you prepare measurements, for example. And also transducers, pitfalls with transducers, pitfalls with signal quality, connections, connectors and cables, front ends and intermediate boxes that can cause different types of pitfalls. And also the applied software firmware. And one of the most important is bookkeeping, and also the validation of results, etc. So the interviews has been summarized in the report with different pitfalls that has been experienced in the nuclear power plants during the years. Okay, so we have interviewed people from Ringhouse, OKG, Forsmark, TVO, and Fortum. And some of the pitfalls that has come up are, for example, related to cables and connectors and sensor pitfalls. For example, grounding issues, sensitivity to temperature or radiation that cause different pitfalls, faulty connectors, all the different kind of pitfalls that could be related to sensors and cables and connectors. For example, impedance issues if you have really long cables and so on. Then also you have pitfalls due to inexperienced personnel and lack of training, for example. And this is also something that it might be avoided by, for example, good documentation and bookkeeping, and also training side by side with experienced personnel that might already have done these pitfalls in their early career and can help a younger colleague to avoid them. Then you have, for example, pitfall using ICP sensors on steam turbines that came from several of the plants, where the sensors are overloaded due to, for example, high frequency content in the vibrations, and this cause different results and high vibration results that caused a lot of question marks at the time. And then you have also, for example, pitfalls due to communication and documentation mistakes that might occur. For example, you have made a structural change or a rebuild in the plant, and this has not been communicated properly with, for example, vibration specialists. And this might cause longer investigation time of a problem. You make the wrong conclusions, and so on. And then also boundary condition issues have come up. For example, when doing modal measurements on steam turbines, and the boundary conditions are never the same during operation as during the modal measurements, and this might cause for example, an unexperienced person to draw the wrong conclusions of the measurements, and maybe when correlating with calculations such as FEM or CFD. And then you have also a pitfall with eddy current sensors on turbine testing, where there was new sensors that were supposed to be changed to an older sensor, and the new sensors were sensitive to magnetic fields and gave very strange results. And it took quite a long time to investigate this and find this. And then, of course, you have the pitfalls due to lack of bookkeeping documentation, where the previous measurements positions, where were they, what sensors were used, what levels were actually measured, and so on. So when you try to do comparison, to compare your results with older results, if the bookkeeping is not good enough, you might draw the wrong conclusions, and so on. So these are some of the pitfalls that are described also in the reports, and that has come up.
Okay, thank you, Jessica. So now I will continue to give you some highlights from the report of like you can have pitfalls by a glance and see it as an appetizer to read the report in more detail. So I will go through shortly here 5 different pitfalls, so you get a feeling of what you can read about. Pitfall number 1 is concerns turbine roll-up when you throttle wet steam flow. You have started with accelerometers, ICP sensors, measuring during the throttling range roughly between 300 to 1100 here. And as you see here, you have up in the upper window here is the amplitude in millimeter per second. And in the lower graph here, you have a phase. And as you see in this RPM range, you have a random phase. You see also that the total level is much above the natural unbalanced forces from the first level. It's below here. But then after the throttling finished, it works perfectly well here. Then the total level is controlled by the natural unbalanced forces one times the revolution. And what's happening here? Yes, you have a very the steam will excite the high frequency, and when you use the accelerometers, you know that they are linear up to a certain range. Then they have this very high resonance peak. So in this wet steam flow, you will excite and overload the sensor. So what they did here to work around is that they changed to the velocity sensor. which is less susceptible to high frequency noise. And they got the run-up working for the full speed range. Next case here is an example of comparison when you have problem with a ski slope from your vibration measurements. You see the red curve here. You cannot trust the low frequency range here. In order to investigate this, we have a pump here, which is driven by a motor. And standing on the foundation here, the foundation and the external pipes causes shocks to the system, so it will be a lot of transients. And this ICP sensor will try to catch all the shocks, but you need to remember that in the ICP sensor you have an internal amplifier, a built-in amplifier, which cannot recover often-wise so fast to stabilize from a shock. So it will mess up the data, especially here in the low frequency. But as a workaround, we have here a laser Doppler vibrometer, which is more an optical way, and it's pointing here on the motor and on the sensor. And that works in a total narrow way, and that's a black curve. You see here you can track the low frequency range. The red curve is the ICP. This upper curve here is in the low frequency 0 to 100, and here you have from 0 to 1000. And you see that it's a good agreement also in the upper frequency range with the LDV sensor instead of the ICP. But ICP works perfectly well in the higher frequencies. Pitfall number 3 here comes to pitfalls when you are dealing with peripheral devices. In this case, we had a turbine generator set that we should measure the reactive and active power coming out from the turbine generator, and that you do by measuring the current and the voltage, and then you're measuring the phase lag in between these, the current and the voltage. And depending how big phase different it is, you can decide upon how much reactive power and active power is generated out to the net. We then used standard current sensor, Amflex current sensors, and they are delivered with data sheets, which are specified, like you should have a phase shift about 20 degrees at 10 amperes. But in this case, we were just measuring 2.4 amperes. So you cannot rely on the data sheet. You must do a verification of a phase for a certain instrument, watching a certain amplitude level. So when we verified this, it ended up that the added phase shift for these sensors were 24 degrees. Also, we used an analog isolation amplifier, which was not so much specification into. And that was a really tricky one because that added a very large phase shift. By verification of a added phase shift to the voltage, we could remove that and remove a additional phase shift from the current sensor. And after fixing everything, there were a good relation between the active and reactive power. So you should never take anything for granted. Should not rely on you must check up everything very carefully. A fourth pitfall here is concerning a motor generator set, where we wanted to make life a little bit more easier for the supplier, and they were not so good on alignment. And the reason there, we had found some cups, Vibracon cups, with like a kind of self-adjusting for angle errors. And these were mounted and installed in a proper way, and they should agree with all the requirements. We measured the vibration during the night after the alignment had been performed, and we got, so to speak, the blue curve here. And the blue curve here is in the horizontal direction. But curve 1 and curve 1 and curve 2 is in the horizontal direction, and curve 3 in the vertical direction. And the blue and the red is two different dates. Nothing has been changed in between these two events. And we see that we get a very pronounced peak the first day, but it disappeared the second day. Also in the two horizontal direction, X and Y. And this all ended up that the supplier had put on some grease into this, that it should slide very much, but it was too much grease. So it's lost the friction, so to speak. So by removing the grease inside the cups holder, everything stabilized. But as this was at that time a new product and no one knew so much about it, but the problem was solved. Last pitfall here among the 5 described concerns a pump, a feeding water pump. And here it was a miscommunication between the pipe designers and the foundation designer. There are 2 projects in parallel, so to speak. Very much focus was on the pump and to get a good foundation. But at the same time, there should be earthquake safety hiring effects for the pipes. As you see here, this is how it showed when everything was designed. They have a lot of constraints for the pipes, and this was not so before. And like Rainer mentioned here, the foundation is very important when it comes to design. We had also a rotor dynamic model in this project, modeling the pump. And the pump is very important that both foundation and the pipe supports, because in this case the pipe support becomes more stiffer than the foundation. So it's like an upside down foundation. So that influenced the pump vibrations a lot. Yeah. And to give you a summary, we want to pinpoint that it's extremely important when you deal with vibration. You deal often with a lot of different disciplines, and you should not take anything for granted. Be curious and ask questions. because that's why the pitfalls often pops up, that you take something for granted and don't know that if this is influence your project. Often wise, when it deals with vibrations, you come in the end of the project, maybe too late to recover from a problem, and that will end up with a time pressure, and therefore you don't look up everything in details. When you read our report, we have a whole bunch of different pitfalls in all kinds of forms for different machines, for different signal types, etc. And it can be difficult to find where should I go and read. But in the beginning of the report, we have tried to summarize what kind of fault you see, like for here instance, that you get an unexpected DC component or skis loop. Then you can follow these different chapters and see if something resembles your problem. So that is how you should work with our report if you don't want to read it from page 1 to the end. So that, I think, was our end of our presentation here, and I would like to thank you all for contribute to a lot of different vibration measure pitfalls from the steering reference group here. Thank you very much.
Yes, thank you very much, Åsa and Jessica, for a good presentation, and also, of course, for a very well-performed project and a good, well-written report with high quality, which you can download from the Energiforsk webpage. So thank you once again.
Thank you.
Thank you.
I think we have time for one question here in the main session before we go to the next presentation. Are there anyone who have a question? Yeah, Monica, please.
If you, at least when you look at your examples, it seems that accelerometers are quite tricky, that they can be the cause for many pitfalls. But what are the main advantages with accelerometers?
Yeah, there are many of them, especially there are a whole bunch of different accelerometers, and you should look very carefully when you buy accelerometers, because they have different performance, and you should not think about that this accelerometer works for all kinds of vibrations. But the main benefit with accelerometers, ICP accelerometers, is that they are often kind of cheap, and they do their work very well if you know what you're doing. They are high performance sensors.
Yeah, thank you. Perhaps I can ask just a general question. How was it to work with this project when you're supposed to sort of find pitfalls? And normally you work in a project where you put together guidelines on how you should do. How was it to collect information regarding the pitfalls?
Yeah, it was, to be honest, it was very tricky. But I think we got everything all right after a time. It was kind of tough work to summarize, and everyone should feel comfortable to speak about it. But I think it was we had a very good cooperation in the end.
It's as you say, it's it's not about how to measure, it's about how to avoid to make mistakes, and it's kind of backwards what we're usually thinking. So of course that's been a bit tricky, but really with the contribution from all you the participants in the interviews, it's we got a lot of interesting examples that we could use in the report.
And I think maybe one thing to learn is that it's very important when you do interviews is that you should listen both to more non-experienced user and experienced user. Because if you are very experienced, it mainly end up with that you know everything and have forgotten about all the mistakes you have performed during the years. So it's good to have a variation in the groups to be interviewed, both young and old people with often-wise more experienced.
Yeah, I mean, because normally when you have a vibration problem, you do some measurement, and normally, of course, you trust the results you get, but it's not that always that you go through the measurement and compare it with perhaps some other measurement, and in order to find a pitfall or a measurement deviation. So you have to go a step deeper in order to actually know that you are perhaps not measuring correct.
Yes, and you have to be critical to your data and to view it also with a critical eye to see is this correct if you see something that kind of looks weird.
Yeah. I see we have another question, but please, Adnan, keep that for the breakout session then, because I think we need to go to the next presentation. Hope that is okay with you.
Fine.
Perfect. Okay, then I would like to welcome the next speaker is Elisabeth Blom from the Tremula technology. She will do a presentation on vibration measurement and strategy in analyzing pipe vibration and pipe support damages. And Elisabeth has a wide experience from working in a vibration area for the nuclear power plants for many years. So please, Elisabeth, go ahead. We can see your presentation, but perhaps you haven't switched on your microphone yet. Yeah. Can you try to share your presentation once again?
Is it said? Or?
Now we see it. Perhaps you should go back.
Okay. Yep. Start from the beginning. So,
perfect.
It's a very ambitious title on this one. I saw it. I should talk a little bit of pipe vibration measurements and what to do. And we actually do often measure the wrong thing to consider pipe vibrations and what pipe damages we have. And we have a strategy that will not compare the damages to the measurement we do. And this is a little bit of tips for what to do the right thing. We have a little bit of why and a little bit of what and some recommendations. This one you have seen a lot of times when I have had presentations before. It has looked a little bit different because I have changed company since last time. But it's exactly the same. The conclusion of this is that 8 millimeters per second RMS is pretty good. Everything is going to match that, almost. And then over 20 millimeters per second, you have to be aware of you have a vibration problem. And in between, you have something else. It depends on the situation and the support and what type of damping you have in the system and how the system is designed. So you have to be aware of vibrations over 8-10 millimeters per second. In this case, you have a lot of different types of damages on this. Not all are vibrations. They're due to high loads, but not especially to vibrations. And you get cracks, you get thermal damages, you get too high loads, you get low cycle and high cycle fatigue, and in some cases it's so high transient that you get guillotine breaks, and especially on bulbs. And then aging on the top of all these. So, and you can't measure the same thing or in the same way for all these, because then you not measure the wrong thing. You have to prepare for the issue you are facing, and half the job is done at the fika table. You can't, if you have a guillotine break, it's no use measuring vibrations with a condition monitoring box or something. You have because you don't find the issue to. Yeah. They're always, almost always, good to use different types of vibration measurement or transducers. It can be everything, and I have a little part of showing what type of transducer we actually have. What? There are different sorts of. Okay, is it me or? You have one transducer and you have a continuous system, and use periodic monitoring to find a guillotine break happening. It can work well if it can work if you have a continuous signal and you have a high cycle fatigue. You perhaps can find something with this continuous vibration situation. We can consider something else. One favorite, you have something that you always use. And I mean, Jessica also said before that perhaps it's a good use to try several different transducer types also. And you monitor continuous during known occasions. I mean, if you have a valve test or something, you perhaps have a continuous measurement during that valve test. And then you take your continuous measurement away, and perhaps you do periodic monitoring on the same transducers during the rest of the time. Then you can learn if the occasion you have measured on have any impact on your system. And then you can measure all the time, 24/7, and measure and find what occasion you actually are after, and perhaps find an occasion that can explain your situation. And this is important if you have low cycle fatigue, if you have guillotine breaks or whatever, then this type of measurements have to be done because you can't find it. I have no experience of finding something that gives guillotine breaks with one measurement with a periodic monitoring system. Transducers. We have a lot of types, and this is just a little solution of types of measuring probes that you can use in your work. You have accelerometers, you have proximity probes, you have final sensors, you have lasers, cameras, and Rogowski oils and load cells and whatever, strain gauges, and so. What can I use where? I have a couple of examples. On a rotating machinery, you normally use these three. You have a proximity probe, you have an accelerometer or a velocity sensor, and then you have some kind of tachometer. They normally a laser or a proximity probe. So you have three types of transducers on rotating machinery in the first place. Occasionally, you can do the same measurements, and then you end up using a heat camera, coil for current, and a laser and an accelerometer. And this type of combination I have used for pulse vibrations and quite a lot of times, because you can measure different things. This is actually an example that's not pipe, but it shows that I have a lot of that I can use a lot of different things. I find this picture this morning, but it's an accelerometer. It's a thread transducer. It's actually a coil connected to a thread that you can measure distances with. You have a laser, you have a proximity probe, you have a accelerometer on the rotating machinery, and on the legs on this machine, it's actually a gas turbine, and a laser that is used as tachometer. So all these together gave me the answer in this time. I couldn't have used one of these. I had all of them gave me information that combined gave the result, gave the answer to the problem. And this had been a problem for 30 years on this machine. Then there are limitations to what you can do on an occasion. Perhaps you have to change the transducer type you have chosen because of somebody had put up a scaffolding on the wrong place. This is actually a pump in one of the stations. I couldn't reach whatever I wanted to measure, and in this case I actually measured the wrong thing because the scaffolding was improving the stiffness in the system. And what answer do you want is actually one of the big questions to ask at the speaker table before, because otherwise you can give an answer to a problem that's not wanted. I did that too. This one is a known one. We have presented it quite a lot of time. This occasions, it happens every week at 1 o'clock in the night between Friday and Saturday. It happens, we shouldn't have been there. We shouldn't have found this if we didn't measure. We measure all the time, but trigger the signal on amplitude. We just save the data during occasions when the vibration level was high enough. And we found this, it happens to be a small valve that opened. Everybody has said that but this is due to pump starts and whatever, and closing of this big valve over there, and it wasn't. It was a small valve that induced all of the issues in this case. I have another case here. This is actually a pump or a pipe beside a pipe, beside a pump. And actually it happens that this becomes transient on different places in this pipe system in different times, and it wasn't due to occasion, but due to something else. And we are not finished with this, but we think it's due to bubbles in the system and different temperatures in the system, that we occasionally get a implosion of a steam bubble. The occasion is 2 seconds. So it's the same thing here. We monitor, we measure all the time. We just save if something happens. But if you go to periodic monitoring, you'll probably find nothing and very low vibrations. I mean, normally you have vibrations in the region of 1 G or something. And then you come to this very significant happening, and as a turbine stop. But it happens to be we have this type of transients 4, 5, 6 times during a period of 15 minutes after stopping, after the turbine stop. So we could, and the turbine stop itself wasn't the highest transient. The highest transient came after 3 minutes, about. So you have to measure. If you measure happening, do measure a bit before and a bit after, because otherwise you can miss the occasion. The recommendation from me is measure all the time. Try to measure for a longer period of time. Don't fix your don't take anything for granted. Measure so you can see what is happening in the system, and you get a lot of data, and it's the bad thing is to evaluate everything. But if you can come up with something that you can solve, you can find the highest peaks in a series of files, then you have come quite a long way. Try to choose what you should use on site, but have a plan B, because it's not not every time you can do as you have planned, or rather, it's usually 50-50 if you can use what you had planned and not. So, and have a few different options. In a system we measure now, you can't measure with accelerometers on a valve, directly on the valve, but the accelerometers are better on the pipes. It's quite good, but on the valves we have to use seismic transducers because of this phenomena also talked about earlier with high frequency sound or vibration. It depends on how you see it, but it's due to the flow. It's flow-induced sound and vibration with high frequency. Beware of the safety restrictions in every. It's different from place to place, so it's not. It can affect your plan. It can go that you can't use the equipment you have planned to use. So you have there your plan C kind of thing. I mean, so I think I stop here. It was quite short, but I think you have heard something about this before, and I'm open to questioning it instead, because I think there can be one or another question on this. Thank you.
Yeah, thank you very much, Elizabeth, for a nice and informative presentation in this area. And it was interesting to have a sort of a recommendation of what to think of when you're doing measurement after we have heard the presentation on pitfalls. So yeah, very interesting. Are there any questions for Elizabeth? Please. Yeah, please, Ryan Norman, go ahead.
Yeah, Elizabeth, I have a question regarding the interpretation of your measurements in time domain and frequency domain. My question is, do you usually use the double-sided frequency spectra with forward and backward frequencies? And does it help to interpret your result better in case you use on the one side only the one-sided frequency spectra or the double-sided? So it could help, I think, to interpret better the results. How is your experience with that?
Depends on what it is. Pipe, a pipe vibration, that's not so much double-sided. It hasn't helped me that much, but in rotating machinery or close to rotating machinery, it can be very useful. Yeah. But the double-sided frequency spectra is a little bit of an learning curve to show to a person outside the vibration specialist group. And I use, for my own sake, I often use ODS to understand the motion in the system and how the system, how you can use it. So I'm using more ODS and more histogram statistics to evaluate vibrations. Then I use double-sided frequency spectra. But when rotating machinery is involved, it can be very helpful.
Yeah. Okay. Thank you.
Okay. Thank you for that. You mentioned, Elisabeth, that it's good to have different type of sensors and measuring equipment when you do a measuring on vibrations, but perhaps on some cases it's because you're interested in different phenomena in the system. You would like to capture different things, but how often and how valuable do you think it would be to, for instance, use a velocimetry and an accelerometer in order to measure the same thing that you're interested in? What can you learn from that?
I think it depends on a little bit what you have, the results or the damage you detect, or it depends what you are using. But often in nuclear you have one shot, you have one occasion to measure your thing, and then to use one type of transducer can be a little bad karma, I say, because then you measure one thing and try to measure in different ways to get a result that is reasonable, and you not always know what you're actually going to see. So it can be, I often, if I know it's a one-shot measurement, I use a camera. I perhaps use a IR or camera, a normal camera, and GoPro is really good. Some lasers to measure distance, load cell, and some type, one or two types of vibration measurements. And just for having, I mean, measuring channels is normally not an issue. It's the measuring what you're actually going to find that is, let's say, which type of transducer you want. Temperature is quite good to involve in this type of measurement, because it can affect very many things.
Yeah. Okay. Thank you very much. I think we have time for perhaps one more question in the main session. I mean, otherwise we can proceed to the parallel session. We can have a more in-depth discussion at the parallel breakout session, both also